Hi, welcome to our presentation. We'll be presenting on dynamic optimization of hybrid energy storage systems for microgrid applications on our course Advanced Power Systems Engineering. My name is Emmanuel and my colleague Darim, and our course instructor for this course, Dr. Ashraf Ali Khan. The increasing use of renewable energy sources such as solar PV and wind turbines in microgrids necessitates efficient energy storage solutions. Renewable sources are inherently intermittent, causing fluctuations in energy supply. Hybrid energy storage systems, or HES, combine batteries and supercapacitors to balance energy supply and demand. Battery provides long duration of storage, while supercapacitors deliver rapid response, quick, fast recharge and discharge. While this synergy improves microgrid performance, optimizing the size and the operation of the HESS remains a challenge, and our project aims to address this. So here's a quick literature review. The hybrid energy storage systems are vital for microgrids with significant renewable energy integration. They address the intermittency of sources like solar and wind by leveraging batteries and supercapacitors. Optimization techniques like the mixed integer linear programming and model predictive control are used to enhance efficiency and minimize costs. These techniques also mitigate battery degradation and extend lifespan. Future advancement in control algorithms, solid-state batteries, and decentralized systems will further boost the hybrid system's performance. So what are our objectives of this project? And the primary objective is to develop a dynamic optimization model for the hybrid energy storage systems, which balances energy generation and demand in the microgrid. Our secondary objectives will be also to try and optimize the charging and discharging cycles based on the fluctuating energy generation from the renewable sources and energy consumption. We'll also try to minimize costs and improve the lifespan of our storage systems, the batteries and the supercapacitors. Our modeling, we added a battery of capacity 10 kilowatt hour and also supercapacitor of capacity 3 kilowatt hour, and we integrated this into our grid or to our system to help balance when we don't have enough energy from the renewable sources. We've placed some constraints on the system that we've modeled to ensure that energy demand is always met, and that is the formula here, which stipulates that the energy generated from the renewable sources and the energy from the storages, the batteries and the supercapacitors, and then minus the load demand at that time period, and this gives us the general demand or the general energy we must supply at given times, and this must always be available. We also set battery and supercapacitor constraints to ensure that there isn't overcharging and discharging, and that means that the state of capacitance or the battery must always be in between the boundaries of the minimum charge and the maximum charge. We've also set the power constraint to ensure that we don't discharge beyond 20% or recharge beyond 90%. This is to help preserve the battery and the supercapacitor health. So here is our energy profile for our system, and the line in blue shows our load profile throughout the day, peaking around the midday from 12 to around 14 or 2 p.m. And the line in the orange line shows us the energy profile for the solar, giving us like a typical simulation of how a solar PV behaves peaking up around midday when there is a lot of sunlight. And then the green line shows us the behavior of our wind energy, which is erratic as one would expect from a wind energy supply. So this serves as a baseline for the data and for the modeling that we'll be carrying on out for the optimization of the hybrid energy storage system. So in our modeled system, we observe two key scenarios: the energy shortfalls, which we see in the red, and this is where we don't have sufficient energy from the renewable sources to meet the demand. And also the green highlighted here is the surplus, the energy surplus. So we have more renewable energy from the renewable sources, and we have the red lines where we have less of the energy required to meet demand for the day. So we'll be trying to solve this efficiently by integrating the battery and or supercapacitor into the system to balance the supply and demand. So in our first approach to optimization, we just included the battery and the supercapacitor without accounting for the recharge. That is the green sections in the previous slide. And here we can see that yes, in the initial part where we have some deficiency in our supply, the battery and the supercapacitor play a crucial role in accounting for this. We minimize the use of the grid up to the point where they get fully discharged to 20% for the battery and 20% for the supercapacitor, and then the grid kicks off. So we still use significantly another part of the grid to meet the demand where we don't have enough supply from the renewable energy storages, and the grid kicks in to supply this deficit. In the second scenario, we have that we accounted for recharging, and upon recharging, where we have the surpluses at this point here, where we have the energy we get from both the wind and the solar is sufficient, and then we have surplus. We use this energy to recharge the supercapacitor and the battery, and then we discharge them when we get to those points where we don't have sufficient energy, and then we're able to minimize a little bit use of the grid, and that helps us to optimize the system a little bit more with less dependency on the grid when we have a shortage in energy supply. So here we tried another optimization approach, and that is using the time of use TOU. Let's say we know the prices or able to predict the prices. We try to optimize the use of the grid when the prices are low, and less of the grid when the prices are high. At this point where the prices become high, we tried as much as possible, if all the systems meet the demand, we try to use more of the batteries and then less of the grid. And even with this method, we still see significantly less usage of the grid energy, and this would definitely reduce cost, as we'll see in the next slide. So in order to put our words into figures, we did a comparison of the price and the cost that we incur by the systems. So we have a cost without optimization, which we get by multiplying the load by the prices, and we can see that we get 1,409 cents usage from the grid, and also the cost without optimization, that is by adding the battery and supercapacitor to our system to account for demand and supply, and we see a significant reduction in the price to about 333 cents. And also from our time of use optimization, our second approach to optimizing the grid system by predicting the prices, using the grid when the prices are low, and less of the grid when the prices are high. And we also make very good savings by doing so, 361 cents. So in conclusion, our project demonstrates that hybrid energy storage systems combined with dynamic optimization improves microgrid efficiency, reliability, and sustainability. By managing renewable intermittency and reducing operational costs, the HESS offers a scalable and cost-effective solution for diverse applications, paving the way for more sustainable energy networks. Thank you very much for listening, and have a great day.